know. I gotta share that. I don't know. I keep wondering if the YouTube stuff popped up. I don't know. I'm gonna have to double check that. Nonetheless, we'll post this so you guys can see it at your leisure. This is the equation we want to solve, and we can solve this in general. So this can be solved. So usually in math class we call it using an integrating factor, but the trick is to make the left-hand side look like a derivative, and then that makes everything work. So you're going to multiply both sides. Well, what was it? The integrating factors, you integrate e to the 1 over tau dt. And what does this become? Well, this is just e to the 1 over tau t. So if I multiply both sides by that, what you end up getting is you have dv dt times e to the 1 over tau t plus 1 over tau e to the 1 over t, or tau t, and then of course you have your v, and then that's equal to e to the 1 over tau t times f. So the key thing to notice, and for those of you who had me for Calc 2, you would go back in your notes and see this, and some of you didn't have me for Calc 2. I don't remember. It's all a blur. But the left-hand side is a perfect derivative. It's nothing more than v times e to the 1 over tau t prime. That's what it is. That's exactly what we have here. So how do you get rid of a perfect derivative? Well, you integrate. But we have to be more careful here than, when we were just little kids, and I shouldn't say kids, when we're little babies, when we're little, I don't know, what do I always call you? Like little wearing diapers in calculus. We kind of just blindly said, okay, here's what we're going to do. Let's integrate both sides now. But if you want to do this properly, you need to be thinking about the fundamental theorem of calculus. And how that kills the derivative. So before we do that, does anybody have a question? So don't forget we have some initial condition, what we call v sub 0 equals something. This was an initial value problem. So here's what we're going to do. We're going to be very, very careful. So I want you guys, and this is something you might not have thought about when you were in differential equations or Calc 2. So I'm going to integrate both sides. From 0 to, let's say, some capital T. So this is going to be, again, so capital T is just some variable now. So you got to be careful. I have lowercase t's. That's my variable. Capital T is a variable, but it's a fixed one right now. So that when I say this is a little higher level than we're used to, that's kind of what I want you to think about. We have to have context of everything at all times. So when I integrate from 0 to t, capital T, what happens? Well, the left-hand side becomes what? Well, by the fundamental theorem of calculus, what do you get? So be very, very careful here. So the left-hand side, by the fundamental theorem of calculus, I get v of capital T times e to the 1 over tau times capital T minus v of 0 times e to the 1 over tau times 0. And then the right-hand side is just the integral from 0 to capital T of this. So, okay, great. Well, what happens to this? Well, this is just equal to, of course, we know e to the 0 is 1. So e to the 0 is 1, so all that's left is v of 0. And we know what that is. That's our initial potential. That's our resting potential, which is v sub CL. So if I rearrange this equation, that is, if I take this guy to the other side, I get an expression for v. So let's do that. So I have v of t, capital T now, e to the 1 over tau times capital T is equal to what? Well, it's equal to v sub CL plus the integral from 0 to capital T of e to the t over tau. Yikes, there's a lot of happening here. F of t dt. So let's be very careful. This is a capital T. And then if I divide everything through, I can get v of t. So what happens when you divide through? Well, this just becomes the constant v sub CL. This becomes e to the negative capital T over tau. And then I'm going to, what you can do, and this is what I really want you to verify on your own, is I can take this e to the, there's no little t in here, so I'm going to take it inside the integral. So what do I have? It becomes minus, so I have e, then I have little t minus capital T over tau, and then this is f of t. Yikes. I mean, this is heavy, right? This is, most of you are not that used to doing these equations and solving them in general where all these constants are floating around. Most of you are used to just solving these when tau is a number and f is some simple function and v sub c is a number. But now when we're applying it to science, we want these constants, these what we like to call parameters, we want them left in there because we want to see what happens when these parameters move, when they become different values. So this is a very, very general way of writing the solution of that differential equation. So does anybody have a question? I mean, this is heavy. Don't get overwhelmed. Don't get nervous. Don't say, I got to change majors. Take this as a challenge. Does anybody have a question, comment, concern? I'm not done yet because I got to plug in what F is. I didn't do that yet. Don't get your little t's and your taus confused. This is heavy. Don't get your little t and big T confused. Okay, now I'm going to plug, what I'm going to do is I'm going to plug what F is into this expression. So what is F? Well, we told you it's this V sub CL over tau, and then it's plus your I, your current input, your stimulus, divided by the surface area over Cm. Or I guess we were using what? C. Okay, yeah, that's fine. All right, so does anybody have a question up to this point?
Is the GCL and CM the same thing?
Well, okay, no, really, I should be more careful. This might have been what's confusing because I forget how I defined it originally, but here's what you need to know. And maybe this is, it's a good, I'm glad you brought that up. Tau, by definition, is C sub M over G sub CL. So I should have mentioned that. I forget how I defined them when we did it last week. I apologize for that. So there's nothing that's written incorrectly. I might not have used C sub M. I might have just used G C sub L before. I don't remember. Maybe you can check your notes. So tau is you take C sub N and you divide it by G C sub L. So remember, G C sub L is this conductance. And so this C sub N, that's also a conductance, or excuse me, it's a capacitance. So I don't remember if I said that or not. I probably just breezed over that and said, hey, it's like an electric circuit or, you know, a resistor capacitor type circuit. So I apologize for that. Either way, I didn't write anything that's incorrect. I just might have written it two different ways, and that's confusing you. And for that, I apologize. Okay, does anybody have a question about this? Now, I don't want to steal all the fun from you. I really don't. That's no fun. So I did most of this for you. What I want you to do, and I want you to fill in the details now, is you need to what you want to do is you want to show that this ultimately comes down to this. VC sub L plus 1 over AC sub M, this integral. And then this is I. So if you integrate this term right here, distribute this through and integrate this, it'll simplify to that. So that'd be good practice for you to get it. And let me fix this. This is very sloppy. Again, I apologize. This is little t minus big T all over tau. And don't forget, little t is the variable here. In the integral, big T is the variable of the function. So this is also a first for many of you. We're defining a function v as an integral. And we can only write this in a nice manner if I is easy to integrate, as you pointed out, Jingzi. You said that when we first started. Mm-hmm. So if the product of I with this E is easy to integrate, then you can get this in some nice functions. But if it's not, we have to leave it as an integral. So this is what we're looking for. This is, I guess we'll put it on the next page. This is the key observation. So the solution is V of t. So look at the function. The variable of our function is capital T. And in order to compute it properly, we need to integrate this creature, which, as you guys know, is not always easy to do. It would depend on what type of function I is. And so we gave you two, one that's an easy one and one that's a fiasco one. But you can integrate both of them. Does anybody have a question? Comment? Woo. So this is, again, welcome to adult land, as it were.
I think we can go from there. It actually looks pretty straightforward.
Well, you got to be careful, though. So there's two subtleties here. In problem 2, you have to be careful how you integrate it. Remember, the I changes. So you have to, your solution for, so here's some ways to think about it. Your solution for part 2 is going to be a piecewise solution. It's going to depend on where t is. So it's going to be, you're going to have t between 0 and 3, then you're going to have t between 3 and 23, and then you're going to have a third solution when t is bigger. And then what we'd like you to do is calculate all 3 of them and then plot them. And you're going to see a nice, pretty cool picture that is, well, remember, if you go back a couple classes, we said our goal is to try to reproduce what experiment shows. This sort of, we see this, what we call the potential, the firing or the action potential, where the voltage jumps up and then comes back down. We would like to try to mimic that. And so we told you here is a very elementary model. It's not going to be perfect at mimicking it in all scenarios, but it's good in some, not all. And as you pointed out, Jingzi, there's much more sophisticated models, which we will get to, the famous one being the Hodgkins-Huxley model, which is more than one equation. It's actually a system of equations. But we have to start baby. We have to understand the simplified cases like this is, and then we build from that. And then for problem 3, as you would imagine, look at your current. Your current is a sine. So that might bring you nightmares that you're going to have to integrate E times sine. And we did that in Calc 2. And if you remember, that is a brutal integral. But luckily, we're not testing you on that anymore. So you can look up the formulas if you want. I won't be mad. Now, if you want to enjoy the brutalness of integrating that by hand, feel free. But you're allowed to look it up. You know, you got software. You have Wolfram that'll tell you what the integral is. But you have to make sure, you know, that you do it properly. And the cool thing is, what we like to do as mathematicians who also want to understand the science is, when we get these solutions, we want to ask ourselves, what happens as t goes to infinity? What happens for different values of tau? What happens for different c sub m's? How does that affect the solution? I mean, think of it this way. If tau was very large, then you would imagine that e is just e to the 0. You could replace it with that, and then you get, then you say, oh, okay, well, if I is a sine, then we're going to get the voltage to oscillate. But you know, so these are kind of, I don't want to steal all the fun. You can think of these things yourself. But, does anybody have a question about this? So let me give you some hints on how to get started. And remember, the learning comes from you doing this on your own, and like I said, asking questions. So let's look at this example. Let's do one. Can't hurt. That's how we learn. I want that color. So let's assume, you know, V sub CL is negative 68 millivolts. Tau, which is the standard one we'll use, 3.33 milliseconds. And then the cell radius is 10 micrometers. So, and then here we'll use a similar I. So you can kind of mimic what we're going to do here. So let's say, let's say the current is we'll say 10/5. So this will be for, let's say 5 less than t less than or equal to 10 and 0 otherwise. So I'm not just making this up. Let's think about an experiment. So suppose I have this cell, and what I'm going to do is for 5 seconds, or I shouldn't say 5 seconds, for 5 milliseconds, I'm going to inject it from 5 to 10 with 10, a current of, let's say, 10. And so that's where I get 10 over 5. That's how you can think of this. And that's how, if you look at the one on the homework, you imagine for 20 milliseconds, I am injecting it. So in order to solve this, we have to be very careful on how we do it. You know, so assume that t, you know, assume that, okay, so let's think about this. When I is 0, so that integral, think about your integral. So what's going to matter is that integral. So look at the integral that we're interested in is this guy, right? So it's not always as easy as you might think to do this. So what is this going to be equal to? Well, it depends on what t is. So if t, so let's say this is going to be 0 if capital T is less than 5, right? Because if capital T is less than 5, then there's no current yet, it's 0. So you just get the integral of 0. Well, okay, let's be more careful. I kind of misspoke. That's not. So let me say it this way. So I'm kind of misleading. Let me say it this way. So look at this integral when t is less than 5, when t is greater than or equal to 5 and less than or equal to 10, and of course when t is greater than 10. So you have to look at this in 3 different scenarios. And remember, graph this thing. I mean, if you want, graph what the inside of that integral looks like, e to whatever I is. So you got to be subtle here if you want to get this problem correct. Does anybody have a question or a comment? I wish we were in a classroom. It'd be much more fun for us to work through this together. We just can't quite, it's just not the same experience sitting here writing it on this board because we can't interact the way we'd like to. So I feel bad about that, but there's not much we can do about it. Does anybody have a question to this point? Okay, so let's think about what this means. So for t less than 5, what's this integral look like? Well, it looks like this. For t less than 5, you have this, and then it's this, of course. Now, here's what you have to understand. For t less than 5, that's capital T. what is little t? Lowercase t ranges from 0 to t. So this means that little t is clearly greater than or equal to 0, but it's also less than 5. Because the integration, the domain of integration is from 0 to something less than 5. So this, of course, equals the integral from 0 to t of 0 dt. And okay, so what's the integral from 0 to t? Now, don't get confused. I mean, think about it. I don't want to say it's easy, but it's also there's that many places that you can actually make an error here if you go too quick. Of course, you know, if you think about it, it's just constant minus constant, or whatever you want to say, and the answer is what? It's 0, right? Another way to think of this is, what is the area of a rectangle that is length is t, but its height is 0? Well, it's 0. Does anybody have a question about this? All right, now, what happens if t is between? So if cat, my house is like falling down. So what does this mean about the variable integration? If capital T, if our upper bound of our integral is between here, then our variable of integration is what? Little t, the smallest it can be is 5, and the largest it can be is 10. Okay, so what happens to the integral now? Well, here, you have the following. So for I of t, do I just plug in what it is? It's 2, right? Well, we have to be careful here. We have to ask ourselves, how is this going to work? How do I look at the bounds of this integral? So the smallest value t can be is 5, and the biggest it can be is 10. So first off, let's double check what I wrote actually makes sense. And one of the difficulties here is I'm using t in 2 different contexts, which is only compounding the difficulty. So what do we have to do here? How do we handle this integral? So one way to help get a grasp on it, assume, let's just pick a physical number for big T. Say 6, just to see what's happening. So what you're going to do is you're going to think of this as, here's how I would encourage you to think about it. The integral from 0 to 5 plus the integral from 5 to t. Does that make sense? And then if you want, you can say, okay, well then this is also the integral from, say, t to 10. But that's not really the case because we're integrating up to just a t, so we have to stop here. Does anybody have a question about this, first off? Remember, 5 is going to be less than or equal to big T, so I have to do it this way. Now, what's nice about this is this integral goes away because we know that when t is less than 5, I is 0. So this guy goes away. This is the only guy that matters. So this is e to the t minus capital T over tau. And then this is, of course, I. So now you have to integrate from 5 to t. This is just 2 times this. Because I'm replacing I of t with 2, because that was 10 over 5. Which this is not a difficult integral. You're all capable of doing that. But let's do it anyhow since there's lots of letters floating around. So if I go to the next page, I'm going to rewrite this. This is 2 integral 0, excuse me, not 0, 5 to capital T. And then this is e. I'm going to break this into 2 guys. This is e to the little t over tau. And then it's e to the minus big T over tau dt. And the reason I'm doing that is because I can pull, the guy that doesn't have little t can come out. So I can write it like this. Lots of little letters that look to be the same. But when I integrate this now, this is not a difficult integral. How do you integrate e? So you 1 over. So this becomes tau. E to the 1 over tau t evaluated from 5 to capital T. Which of course becomes 2 tau e to the negative t over tau. Now plug in capital T. When you plug in capital T, you get e to the negative capital T over tau. Excuse me, e to the it's positive. And then minus e to the 5 over tau. Which of course, if you distribute this back through, you're left with 2 times tau. And then when this becomes 1, because e to the 0 is 1, minus, you can recombine this. You can combine this as 5 minus capital T over tau. So I'm doing lots of math in 1 or 2 steps here. So you might really want to take your time with this. That is something else, isn't it? Woo! I feel for you guys. Learning this is such a pain. I'm just kidding. This is so much fun. Does anybody have a comment or a question? Does anybody want to scream at me for making you learn? Not making you, but asking you to learn this. This is fun, huh? Anyhow, woo, that is something else, isn't it? All right, great. So that's the second integral. Now the third we have to do, now we're saying that capital T is greater than 10. And so that means, of course, if capital T is greater than 10, well, little t can still, you know, where can little t range from? Well, that can range, again, from 0 all the way up to capital T, obviously. And let's look at this integral. From 0 to t, e to, of course, it's t minus capital T over tau, I of t. But remember, when t is bigger than 10, we're not interested in what happens. So you could think of this as equal to the integral from 0 to 10, and then plus the integral from, say, 10 to t, because I is going to be different on each one of those intervals. Matter of fact, we have to be even more careful. We have to integrate 0 to 5, plus 5 to 10, and then plus 10 to t. So I don't know if this is anything that you guys have sort of thought about before when you're integrating over. I mean, remember, our function we're trying to integrate, its rule depends on the domain we're on, because it's a piecewise function. And similar to in the previous problem, this guy is equal to 0, so we don't have to worry about it. This guy turns out to be equal to 0, so we don't have to worry about it, right? Because if you're integrating on this interval, we know when little t is bigger than 10, this is going to be equal to 0. And so the only integral we must consider then is the middle one. So this is just 2 times the integral from 5 to 10 of e to t minus capital T over tau dt. Again, the 2 comes from, that's the value of I here. Yikes.
Can you explain how you get that range from like 0, t is greater than 0?
Okay, I'm choosing that because if you go to the original diagnosis of the problem or the original statement, yeah, go all the way back here. The times that matter are 5 and 10. So before 5, I is equal to 0, right? And so after 10, I is equal to 0. So the reason that I broke my integral up into these 3 pieces is because, notice the blue line here, that's because the integral is equal to 0. Here, on this integral, I is equal to 0, and on this integral, I is equal to 0, which means both integrals are 0, so I don't have to worry about them. This is just one way to reason that. You might come across the reasoning on from a different perspective. This is just how I'm reasoning it. So I need to know, remember, I have to compute this integral for all values of t. And so since I depends on where my little t is, I have to take each one of those situations and look at them separately. And maybe when we're done with this, it might make a little more sense. And let me also reiterate, and Abdullah, this is a lot for you today because we went over how much all the octave stuff, then this, it's very overwhelming, I'm sure. But when we put this all together, I hope that you'll take the time to go through this. And it's look, this is not easy math. This is not, this is a higher level of thinking. It's much more complicated calculations. But if you want to know what certain people do for a living and what kind of, you want to see a glimpse into what we call mathematical neuroscience and research, what people do, this is it. So you're not going to get this. It's just not going to make sense to you in 20 minutes. There's a reason I gave you basically 3 problems on this homework. I mean, these are complicated calculations. Although once you master them, you'll see how easy they are. But until you master them, they're not easy. They're very overwhelming. Okay, once again, you think about how you might integrate this. And there's a couple ways you could do it. You could do what I did in the previous one where I separated the exponentials and then integrated and then put them back together. What you're going to find, though, is that I'll let you do. Let's see if you can get it. What you're going to find is this is equal to 2 times. Look, just like in the previous problem, in the previous term, we had 2 tau, blah, blah, blah. If you do this properly, you're going to get 2 tau. And then it's going to be e to the 10 minus, or get it backwards here. So let me be consistent with what I had before you have minus t. So it's going to be 10 minus t, capital T, over tau. And then this is minus e, and it's going to be 5 minus capital T over tau. So you should fill in the details of that. Make sure you get the same thing I got. We're almost done, I promise. This is a lot, right? Okay, so we can put the pieces to the puzzle together now. So let's do that. Let's put the pieces together. Here's what we can conclude. So what are we concluding? Well, we know our function v of capital T is v sub CL, right? And it was plus this 1 over a c sub m, and then it was this integral. And what is this equal to? Well, we just figured out that it's piecewise. So if we put our pieces to the puzzle together, it's 2 tau out front over a sub cm. And then what did we find? Well, it depends. It's going to be 0 when t is less than 5. It's going to be 1 minus e to the, what was it, 5 minus, let me write this bigger. It's really hard to look at like 3 screen. So this is 1 minus e to the 5 minus capital T over tau. And this is when capital T is between 5 and 10. And then the last one we found was e minus, or e raised to the, 10 minus t over tau minus e raised to the 5 minus variable over tau. And this was when t was greater than 10. Woo! That is brutal. Are you guys having fun yet?
Yeah, it seems doable.
Look, it is. It takes a while to learn this, though. This is a calculation. Look how many places we could have made an error.
Uh-huh.
I mean, it's just, that's the nature of this. These are delicate computations, and, you know, practice is the key here. Now, what's interesting about this is we could, let's plot it for the numbers I told us to plot it for, right? So let's go to Desmos. Why don't we? Or I guess I could do this in Octave, but let's go to Desmos and graph this. So let me pull this up for you. So here's the problem with Desmos, that the reason I would always encourage that you use Octave is because with Desmos, it doesn't like V's and T's. Everything has to be in terms of like y's and x's by default. So let's look at our function. So I'm gonna call it y because I don't know what else to call it. And then what's our v sub cl? It's negative 68, right? Isn't that what we told you to use? Negative 68, and then it's plus this 2 times tau. So let's say 2 times, what was our tau? 3.33. And then that was divided by our area. We'll tell it what area is in a second. And then it was cm. So we'll just leave, we'll get to that in a second. Now, the first part, I guess I should be, okay, so then let's do the first part. The first part is this times 1 minus e. Yikes. And so what we have to raise this to a power. So what was it? It was 5 minus variable. So this is going to be, what I'm going to do to, well, okay, let's, so it's 5. It's going to be over our 3.33, but it's 5 minus the variable here. So this is one piece. And what piece is this that I'm doing right here? This is the piece 5 less than or equal to x less than or equal to 10. So we got to tell it what a is. And what did we want a? We want that constant underneath to be. What was the surface area? What was it? I don't even remember. What did I say it was? Does anybody remember what we chose for our what was our
The radius
constant
was
for
10
A?
micrometers.
What was it?
You just wrote the radius 10.
Yeah, what was the radius?
10.
10. All right, so then let's say, okay, so give me 1 second before I don't want to misspeak. I mean, it doesn't really matter. Let's just say, for the heck of it, just say, let's just put point, let's just call it 1 for now. It's not going to hurt anything. All right. We'll adjust that in a second, but let's look at what the graph looks like. Notice you don't see it, but of course you don't because it's going to start down here at negative 68, right? So look at the shape of this graph. Look what it looks like. I'm going to thicken this. Now, of course, there's nothing here, but we know what the function is. We know it's equal to 0 between 0 when the input is between 0 and 5, right? So here's what you imagine. I'm sorry, not this. It's negative 68. So here's what happens. This green part is the resting state. Nothing's happening. And then what happens at 5 seconds? At 5 seconds, we start stimulating it. So the voltage begins to increase. And then what happens at 5 seconds? Well, we have to plug that creature in. So it's similar to this. So let's just duplicate it. Only it's slightly different. So this will be for x bigger than 10. And what was it? Well, we know the first piece was e to the 10. And so what you're seeing is a very nice, let's change the color here so we can get real agreeable. So look what happens. And this, if you think about it, this is what maybe your intuition thinks happens. So let's look at this screen. The cell's chilling there in the green. We start the clock. It hovers around its resting state, negative 68 millivolts. And then at 5 seconds, or 5 milliseconds, I guess I should say. At 5, and then this is 68. Right when we get to 5 milliseconds, we start our stimulus. And what happens is it starts increasing. The voltage increases. And then what happens at 10? What is that? Whatever that point is. Negative, say 64. I know. So right around this black dot, right around here, then we stop the stimulus. And so look at it exponentially, the voltage exponentially goes back to its resting state of negative 68. So if you look at this, what's nice about this particular model is it actually gives us it matches experiments for certain types of voltages, or at least certain types of stimuluses, I should say, in many cells. But it took us a lot of work to get to this, did it not? So does anybody have any questions about this? Comments, concerns? Now, watch what happens if I change this constant that I had before, this A. You know, let's just say A changes around. You see the shape of the graph changes a little bit. So depending on what these constants are will affect how this works. You know, for large values of A, it starts to flatten out, as you would expect. Imagine tau, and then you take smaller. You know, what if A, for example, is 0.003? Well, now you have, it's huge. If it's just, look what happens when you have this value of A. Now you get this sort of shape. Anyhow, does anybody have any questions or comments? Concerns? Want to complain about anything? So hopefully you guys can do this. It's going to take some time. You're going to mess it up at first. That's part of the fun. That's how you learn. Does anybody have any questions?
Can you post relative files regarding this part, like?
Yeah, absolutely.
Because I want to kind of look on the books and see, like, while I was searching on the internet, it's kind of like.
All right, you got to be careful what you look for because you can end up getting way more confused than you want to get. Yeah, I'll post some files over the next day or so on.
Okay, perfect.
Okay.
And
I'll even write a file to graph this on Octave.
Oh, okay.
Because it's much easier on Octave than it is on Desmos.
Okay.
All right.
Yep.
Any other questions? Comments, concerns?
Dr. Grady?
Yes.
For the homework one, I down the first, second, and third questions, and the fourth question I used the euro to solve. I haven't finished that yet.
Yeah, that's fine. So like I said earlier, if you just want to submit the first parts, the ones you can do by hand, that's fine, and then worry about the computer ones later. Don't worry about that right.
Is it okay if? Oh, sorry. Is it okay if we do the homework one, just completely submit you a MATLAB file, because I can just probably like make some notes on there for the definitions.
Yeah, that's fine. However you feel best to submit it, and if I'll comment and let you know if you need to change anything or do it differently.
Oh, okay. Sure.
Yep.
All right.
Okay.
Does that answer all your questions?
Yep.
Yes.
All right. Well, listen, and we will talk again Wednesday at noon. I think, yeah. And then, Jingzi, I know you. I owe you an email, I believe, right? And then we need to talk.
Yeah.
Or did you figure that out already?
We can probably talk after Wednesday, because I want to see how far I go on the MATLAB.
Okay.
Because
all right, great.
I had no problem doing the